All right, good morning, guys. We are on topic 4, SAS 3, exploring quadratics and cubics, and it is on page 93 in our workbooks. So, it says, in the previous exploring, you used a third-degree polynomial function to understand how changes in luggage dimensions impacted volume. All right, you know that f of x equals x, or also known as y equals x, is a first-degree polynomial function because that x has a first degree. Then it says f of x squared is the simplest second-degree polynomial function, okay? What is the third-degree polynomial function? Y equals x cubed. All right. So what I'm going to do now is you see I start out with y equals x squared. All right. So if I start changing all of these parameters, I end up getting a cubic function. Okay. A cubic function looks like a snake. It can always increase, it can always decrease, it can increase and decrease, or it can do it all, okay? So, on your page, number 1, it says, sketch a graph of a cubic third-degree polynomial that always increases. So, I want you to draw me a graph on all 4 spots. Okay? So, let me pull up our calculator. All right, in our calculator, in our y equals, I'm just going to type in the simplest third-degree polynomial, and that will be x cubed, okay? And then I'm going to hit graph. What do you notice about this specific graph? Well, it's always increasing. Okay? It's always increasing. Now, how could I make that always decrease? We can put, not squared, we can put a negative out front. So now we're going to go to our calculator and we're going to type in negative x cubed. We're hitting graph. So you notice that it is the same graph that we just did, except this time it is decreasing. All right, now C says it does not always increase. So if it is not always increasing, then it can also be decreasing. So I've just made up a random cubic function. And it starts with x cubed minus 2x squared minus 3x minus 3. And I'm going to hit graph. Now, you'll notice that this graph first it increases, then it decreases, and then it increases again, right? So it was y equals x cubed minus 2x squared minus 3x minus 3. Now, this is a cubic function because the highest power or degree is 3. And we talked about that yesterday. The highest degree, highest power is 3. So this is a cubic polynomial, also known as a third degree polynomial. Okay? So now I want to do one that does not always decrease. So I'm going to change it up a little bit, and I'm going to say negative x cubed plus 2x squared plus 3x plus 3. So I kind of just changed all the signs. So now I'm going to hit graph. And you'll notice it's the exact same graph, except first it's decreasing, then it's increasing, and then it's decreasing again. This graph is y equals negative x cubed minus 2x squared minus 3x minus 3. This is also a third degree polynomial. Okay, it has a constant term of negative 3, and the leading coefficient right here, would that just mean negative? Like just my coefficient is just a negative? No, what is that number that's there that we don't write? A 1. So my leading coefficient would be a negative 1. Okay. I went ahead and hit the green arrow, and we are on page 2 of Agile Minds screen. So it says, as you worked with the animation on the previous page, you might have noticed similarities and differences among polynomial functions of different degree. Unlike linear and quadratic functions, there is no single way to describe the behavior of polynomials of higher degree. For example, consider the third degree or cubic polynomials graphed here. So if you look here on the left, f of x equals x3 is only, increasing. Now this graph on the right shows that the function increases, and then it decreases, and then it increases again. So there is no set of transformations that will map one graph onto the other. Okay, so there is no single cubic parent function. Okay, you just can't do it. You've got all of the different things. So I'm going to go back one screen. And look, if I move just to the left, it goes negative. And it starts decreasing. But if I take this, it starts to add another curve. So there is no single simplicity of a cubic function. Okay? It can do all kinds of different things depending on the values in front of each term. So, I am going to head on to question 2. And we're on page 94 in the workbook. So, if you look on page 94, you see your graph, and you see the same graph on the screen. All right, so I want you to draw on your graph on your paper. So from the bottom of this graph to this point, it is increasing. Then it starts decreasing from here to here. Then it picks back up where it left off, and it starts increasing again. Okay? So, to find the values of where it increases and decreases, you have to look at the x values. Okay? So, particularly on the left-hand side, it hits where I just drew that green line. And each tick point or tick mark is going by 1 every 2 times. So this first green dot is going to have to be a negative 0.5. Now, my second green line is going to be between, and if I kept drawing that line up, it is between 1.5 and 2. So in the middle of that is going to be approximately 1.75. Okay, so the first blank says f of x is increasing when blank and blank. All right. So it is increasing from here to here. All of these values on the left-hand side have got to be less than. Okay? But what was our green point on? Our green point was at negative 0.5. So, it increases when x is less than negative 0.5. Then, from negative 0.5 to approximately 1.75 is when it decreases. Then it picks up where we left off at 1.75. And all of our values are greater than that. So, here to here, we are increasing. And it stops at negative 0.5. From here to here, we are decreasing, and it stops at 1.75. Then it picks up, and it increases again. All of these values are less than. All the values on the right are greater than. Okay? All right, so now on number 3, it says there are key characteristics of polynomial functions that are closely related to increasing and decreasing behavior. To better understand this characteristic, think about quadratic functions. So what I want you to do right now, you have this chart and this graph on your paper. So you only have your X column on your paper. So what I want you to do is take a minute and copy your Y values onto your chart. Once you are done, I want you to graph X and Y points from the chart onto the graph beside it on your paper. Once you're done, it should look like my graph. Okay, now that you have that done, I want you to notice what it says at the bottom. As the values of x increase to x equals 0, which is right here, the values of the function decrease until they reach a minimum or the smallest value of y equals 0. Okay, so if you look, my y values start with 4. When they get to y equals 0, are they increasing right here or are they decreasing? They are decreasing. Now, as for the x values that continue to increase, you also notice that the values of y increase. Okay? So, right here, since y equals 0 is the smallest value of the function can reach, it is called the function's absolute minimum or global minimum. The lowest point on the graph is called the absolute or global minimum. All right, now we're flipping over. And this time, you notice that your values are swapped. Okay? They are negative. That is because my parabola is upside down. So, I want you to take a couple of minutes and I want you to graph the points in this chart. Once you're done, it should match the red graph. Okay? All right, it says this time as the values of x increase to y equals 0, the values of the function increase until they reach a maximum or largest value of y equals 0. So in this case, this function, f of x equals negative x squared, has an absolute or global minimum. That is the highest point on the graph. Okay? Now look, it says every quadratic function either has an absolute maximum or absolute minimum. You see this max and min value graphically when you look at the vertex of any parabola with a vertex axis of symmetry. So, going to be doodling here. You can just listen. This parabola right here, does it have absolute minimum or an absolute maximum? A minimum. What about this parabola? Has a maximum. Okay? Now, on number 5, it says, give an example of the function other than f of x equals x squared that has an absolute minimum. All right, so if we want to have an absolute minimum, then we want to have the lowest point. So I'm going to take my function, and I'm just going to move my graph down 3. Does this still have an absolute minimum? Yes. 0, negative 3. Okay? Now, on number 6, if I wanted to use something other than negative x squared to have an absolute maximum, I could simply do that too. We can even use the same thing. Right, I can use this same thing, the same transformation, except this time I added something else. I used my negative, and that means it's a reflection. So now I'm still going down 1, 2, 3, but my graph looks something like this strictly because of this negative. So now I have a maximum point of 0, -3. All right. This says, now think about cubic functions. You can say that what can you say about their max and min values? To begin to explore this question, first analyze the cubic function f of x equals x cubed. All right, so this right here, it is strictly increasing. Nothing is decreasing. It even says it increases over its entire domain. Okay, so a domain is an x. Okay, x values run left to right. So you were looking on the left side of the graph. Here's the left side of the graph. Okay, you notice that it is strictly increasing, right? Now, once you move to the right side of the graph, you see that it is strictly only increasing again. So if it's only increasing or if it's only decreasing, there are no max and min values. Okay? Now, here's another cubic polynomial. It's cubic because it has a degree of 3. All right, it says, can you find the maximum value of f of x? The graph gives you a clue. To the right of x equals 2, the graph starts rising, and it continues to rise. This indicates that there is no absolute max value, okay? This is a max value, but we don't have an absolute because do we know where this graph ends? Or do we know what this graph does from here to here? No, we don't, okay? Now, it says, can you find the minimum value of this graph? So we're looking from here to here. The left of x equals -2. It begins to fall, right? So it will continue to fall for that time. Here's a min value. We don't know the absolute because we don't know where the graph goes or where the graph turns. So this is kind of confusing. Let me see what's on the next page. Okay. All right. Now, this is the part you're going to know already. It says, however, something interesting happens in these points. So this is the exact same graph, okay? Notice that the function increases until it reaches y equals 5 1/3. So here's a point, and here's a point. So from here to here, my graph is increasing, right? This is the maximum point. This is called the relative or local maximum. Right here is going to be my relative or local minimum. So when you were looking for min and max values, you were using the term local. Okay? Now, absolute, which is what we just talked about, they are different. This graph does not have an absolute minimum or an absolute maximum simply because we do not know where this graph goes or where it ends. We are only given a small window range of it. So for all we know, it could be going up and back down and up and back down, and we don't know. That's why it does not have an absolute. But it does have locals here and here. Okay? All right, number 7. On your paper, it says, does every cubic function have some sort of max or min value? Well, no, it doesn't, because right here, this graph is strictly increasing. Right here, this graph is strictly decreasing. So I don't really have a max or min value, okay? So for number 7, it is no. Now, for number 10, okay, we're talking about cubic functions. So it says, a cubic function is a polynomial degree of 3. A cubic function has domain blank and range blank. So remember, this is a cubic function, okay? Remember that our domain is X and our range is Y, okay? So, domain, we read left to right. So on the left side of my graph, I'm increasing. On the right side of my graph, I'm increasing. So, if it's all increasing, down here is negative infinity to positive infinity. That can be used as all real numbers. Now, same thing for the range. Range is bottom to top. So I'm looking at my graph and I'm saying, oh, here's the bottom. It's on negative infinity because we don't know where it starts. And on the top, it's positive infinity because we don't know where it ends. So, once again, this would be all real numbers because it covers the entire graph. Okay? Now, it says some cubic function always blank like f of x equals x cubed. Since that's a positive cubic, that's going to be increasing. Then it says some cubic functions always blank like f of x equals negative x cubed. So since it has a negative, we're going to decrease. Some cubic functions blank, then decrease, then blank. Remember, some increase, then they decrease, and then they increase again. Some cubic functions decrease, and then they increase, and then they decrease. Some cubic functions, like x cubed and negative x cubed, have no min and no max value, which is what I just said. Remember, I drew the graph and I said there's no min or max values. But other cubic functions that have an x cubed and an x squared or a constant with it do have local maxes and local mins. Okay? So now you have 3 practice questions to do. Number 7, number 8, and number 10.